Hello, my name is Sai Vamsi Krishna. Uh, Today I am going to uh, tell about what is the criteria for achieving machine dependent optimization. First, we'll talk about what is optimization. Code optimization is a program transformation technique which tries to improve the code by making it consume less resources and deliver high speed. The main goal of code optimization is to achieve better performance. Now, what is the process of optimization? First, the source code is taken from the front end and an intermediate code is generated. In here, machine independent compiler optimization is used to optimize that code. Again, that intermediate code is taken into code generator and target code is generated. That target code is then optimized using machine dependent compilers optimization techniques so that the code runs more faster and takes less space. Now, what are the levels of code optimization? There are two levels of code optimization: machine independent code optimization and machine dependent code optimization. In machine independent code optimization, there are techniques like control flow analysis, data flow analysis, transformation, etc. In machine dependent code optimization, there are techniques like register allocation, loop unrolling, enabling instruction level parallelism. Now we talk about machine dependent optimization. When code is modified to make it more efficient on a particular machine, a machine dependent code optimization is being performed. What is machine dependent optimization does? It is done after target code is generated and the code is transformed according to the target machine architecture. Machine dependent optimization uses information about the limits and special features of target machine to produce code which is shorter or which executes more quickly on the machine. Now, techniques of machine dependent optimization. First one is enabling instruction level parallelism. If two instructions do not depend on one another, they may be executed in parallel. Consider an expression such as a star b plus y star z. The two factors a star b and y star z can be evaluated at the same time as they are not dependent on each other. So, if the target machine allows parallel processing of two multiplications, the compiler should generate code to take advantage of this capability. Also, compiler generating code for pipeline vector machines should take advantage of this machine's availability to perform vector operations in parallel. Next, register allocation. Register allocation refers to choosing the values which are kept in registers during the program execution. Values stored in registers can be accessed more quickly than values stored in other types of memory. Since computers have only limited number of registers, the efficient use of these registers is more important in producing good code. Next, loop unrolling. In loop unrolling is also known as loop unwinding. Is a loop transformation technique that attempts to optimize a program execution speed at the expense of its binary size, which is an approach known as space-time trade-off. The transformation can be taken manually by programmer or by the optimizing compiler. Next, what is the criteria for achieving machine-dependent optimization? Well, one is choose good data structures. A good data structure is used for optimizing the code. Next, reduce number of operations. Use cheap operations like strength reduction. Avoid too many functions calls. Inlining. Use compiler optimization flags. Help the compiler use constant and distinct. So these are the criteria for achieving machine dependent optimization. Thank you.
Now we are going to construct the canonical parsing table for the given example. S derives C, C and C derives C, C or D. Starting with the augmented grammar, which is S dash derives dot S, and the look ahead here is dollar. As the next element here succeeding the dot is S, we need to write all the productions of S, which is S derives dot CC, comma, the look ahead for S is the first of dollar. So as the first of dollar is dollar, the look ahead for this expression is also dollar. And now we must include all the productions of C. Why? Because it was after the dot. So now the production of C derives CC dot CC. It also derives or dot D. As the production of C is because of this C which was in the previous production. Now the look ahead of this expression would be the first of dollar, C comma dollar. The first of C comma dollar is obviously C or D, which is small c, and here also the same C or D. Now this is the first I naught or the first state or someone else. Let us name it as I naught. And now by adding the transition S to the initial state of I naught, we'll get for the first production S dash derives S dot comma dollar. As it is a transition, there will be no change in the look ahead in this production. Similarly, now when we had a transition of C to this state, to the previous state, we'll get S derives C dot C comma dollar. This is because there will be no change in the look ahead of the previous state. Similarly, and now as there was a C expression after dot, we need to expand all the productions of C, which implies C derives dot CC, which is also derives dot D. The look ahead for this is same dollar. Why? Because the first of dollar is always a dollar, so the look ahead for this is dollar. Let it be another state. And now the transition for this previous state, let's give it as small c. Now the following production through transition C gives us C derives small c dot C comma, the which is the look ahead for the previous state is obviously C comma D, C or D, which is not changed through the transition. There is a small expression after the dot, so we need to expand the C once again, which we include the C expression. Now C gives rise to dot C, C or D, which has the same look ahead for the previous one, C or D and C or D. Let it be another state. And coming to the transition of D to the initial state I naught, D, and the following are the productions gained after applying the transition for the initial state I naught, which is C derives D dot comma C or D. Why? Because there is no change in the look ahead when there is a transition. That's it. These, let us name them as I0, I1, some I2, and I3, and I4. Now, similarly, we have to extend all the transitions for all the states which are not final states. As this was a final state, no need of extending I1. Why? Because there was no elements after the dot, which means it implies it is a final state. And similarly, I4 is also a final state. Why? Because there is no expressions to be traversed after the dot. The construction of all the productions is done in a similar way. Starting from initially we have constructed I1, I2, I3 and I4. Now we are constructing the extra productions. After I2, when the production is C, when the transition C is given to I2, we'll get S derives C dot. Why? Because just shifting the dot from one position, and the look ahead does not change, which is similar to dollar. This is small c, and the production small c is given to I2, we'll get C derives C dot C, this one, C dot C, comma dollar. Why? Because look at it doesn't change. And now we need to include the production of capital C. Why? Because it is after dollar, which is C derives dot small c capital C, comma dollar, or it can also be derived dot D, comma dollar. And then coming to the production D to I2, we'll get the last one. C derives D dot, which is the second production in I2, third production in I2. The look ahead will not also change. And coming to I3, there are three states: capital C, small c, and D. All these three are the transition states. When we give the capital C to I3 as a production, we'll get C derives C dot, comma C or D. Why? Because the look ahead doesn't change when we give the production. And similarly, when we give the production small c as a production to I3, we'll get the same state as it is recursive. And then when we give D as a transition to I3, we'll get the same state as I4. And then continuously we have to go on expanding the productions in a similar way. And coming to this state, as it is a final state, there are no expressions to traverse after a dot, and this is also a final state, and this is also a final state. The only state remaining is this one. Coming to this state, we have only two states to traverse, which is capital C and D. When we traverse through, when the transition for this state is D, we'll get C derives D dot, comma dollar. Why? Because the look ahead doesn't change. And coming to the transition C, we'll get C derives C dot, comma dollar. And now this is the final through this we can construct the canonical parsing table by giving we'll just give the numberings for all the states. Let it be I0 and I1, I2, I3, I4, and then coming I5, and let it be I6, and this is I7, I8, and this is I9. Just now, as we constructed the final stage of total 10 states for the construction of canonical parsing table, there are 10 states, basically 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yeah. And there are mainly two states which are action state and go-to state. The action states include C, D, and dollar. All these three are action states. And the go-to states include S and C. Yeah. And now this table is filled by using the previous states, such as when we are in the 0th state, if there is a transition of C from 0, we can directly reach to 3rd state. Similarly, when there is transition of D from 0, we can directly reach to 4th state. Similarly, there is no transition for dollar, for S, and there is a transition for C from there is a transition for C from 0, which gives us the second transition state. As the first is as first yeah first coming to second, there is a transition from C which derives S6, and for D it derives S7, and there are no transitions for S and C, just leave it. For third state, there are transitions from C and D, which are basically S3 and S4. And for the fourth transition state, we will get the reduced states, which are basically, which we name it as R. For these R, for the transition C, for the fourth state, we can directly traverse to third state, and for this also we traverse to third state, and do not of all those. And this coming to fifth state, there is no transition of C and D, but there is a transition of dollar, and now the transition takes us to R1. And for the sixth state, there is a transition of C and D, which derives us to S6 and S7. And similarly for 7, there are no C and D, coming to dollar, which is R3. And for the eighth state, the transition for C is R2, and the transition for D is R2 again. And for ninth state, the transition for dollar is also R2 again. Yeah, coming to the go-to states, the first was filled by us, and there was no second. The first 0th was filled by us, and there was as 1 is a final state, there is no transitions from 1. Coming to the second state, from S there is no transition from. For S there is no transition from 2. For C there is a transition from 2, which gives us the fifth state, and for third state will gives us to the 8th state, and only the one more remaining state is 7th, I guess. Yes, sorry, 6th. 6th is the only remaining state which C has acts as a transition, which gives us the 9th state. That. And hence this is a construction of the given example. S gives rise to C, S derives CC, and C derives CC or D. And hence we constructed the canonical parsing table for this example.